Well, looks like we got a couple people.
Yes. Welcome.
Hello, everyone. So, just in time to get started. Thankfully, we'll skip out on the puns for now. So, as you can see by this little presentation, I hope I can really change your mind. So, today we're going to talk about AKLO, Automated Kinetic Linking Optimization. Now, the name sounds a little generic, but I have got my reason for it, which I'll explain a little in the presentation. So, overview, a bit of the introduction, discussing what brain-to-brain interfacing is, how I intend to implement it, the sequence of steps in pseudocode, the impact it will have, I hope, and the conclusions and some of my references. So, next step. The basis of society is communication, as I'm sure Keith would agree with. Language can sometimes hinder it, because there's mistranslations, like my puns in English don't always translate to French. So, how can we improve this? Now, is it possible to send information directly between brains? Yes. I know there's a lot of hype about invasive implants thanks to Elon Musk and his Neuralink, but overall, you can do it non-invasively, meaning that instead of jamming electrodes into your brain, you can wear a device that doesn't require any surgery, just a headgear. So you could use non-invasive neurostimulation and neural recording to do the same thing. So, experiments by Jiang and Rao, two of those papers there, discuss some of the logistics of it, which I'll get into a little later. And furthermore, Nicolelis, one of the Brazilian experts in neuroscience and brain-to-brain interfacing, showed that you have cognitive enhancement for every brain in the network. Essentially, everything works as a giant biological computer. So, the problem with invasive implants is that it requires surgery, often with materials that are not biocompatible and evoke the immune system response. So, Rao and Lee demonstrated you could have non-invasive brain-to-brain interfaces, which don't require any drilling into the skull, just wearing stuff on your scalp, using transcranial magnetic stimulation, that is, using a magnetic field electromagnet to induce a current inside the brain, right through the skull, and we use focused ultrasound, TFUS. So, a brain-to-brain interface typically requires two parts, the brain-computer interface and the computer-brain interface. The brain-computer interface is well-tread ground in neuroengineering, basically using electrophysiology, the changes, electrochemical changes induced by your neurons. And those patterns get translated via a computer algorithm into controls for a device. In this case, it controls a computer-brain interface, something that would be like transcranial magnetic stimulation or focused ultrasound, to stimulate a particular region of your brain for a particular end, like controlling part of the motor cortex or inducing a flash of light of phosphenes in your brain. Now, a lot of the non-invasive BCI, a lot of the hobbyist stuff uses EEG, electroencephalography, one of the most common forms. But overall, CBI, the two main things I'm focusing on for this presentation are TMS and TFUS, but other ones exist. Now, brain-to-brain interfacing can be limited to one or many users. One user might use it as a feedback system for meditation, for instance. And performance is gauged by the information transfer rate in brain-computer interface, often in bits per minute. The ITR is affected by the accuracy of the BCI system, the number of options and classes that you can select from, like the degrees of freedom of a robot prosthetic or the directions you can move a cursor in, the latency, the time it actually takes to process everything, and the stimulation type. Like focused ultrasound takes half a second, whereas TMS works in 8 milliseconds. So the existing BBIs, like the Rao one that I cited earlier, have really low ITRs, less than 100 bits per minute. That might sound like a lot, but for comparison, writing something on a Post-it note is about 20 bits per second. And two neuroscientists, Lebet and Nertrainers, cited consciousness as having 16 to 20 bits of information per second that helps determine your decision-making process. And even a low brain-to-brain interface can affect decision-making activity, potentially. But that has some scary or interesting implications down the line. Now, EEG brain-computer interface are routinely made by hobbyists and used in the industry and medicine. Computer-brain interfacing can improve has also been used to improve training. Like in this case, in this study, it's been used to improve pilot training by up to a third. And EEG BCIs are used in drowsiness detection in industry and transport. So can we combine these two together in real time for meaningful outputs? Yes. So devices and parts for EEG are getting simpler and cheaper. For example, the Open BCI is a hobbyist grade EEG-based brain computer interface that I've used extensively in some of my prototypes. So ways to make brain-to-brain interfacing more accessible. You could have safe, reliable computer-brain interface, which is the topic for a different discussion, but also a standard software protocol, maybe something based on Internet of Things protocols that are already in use around the world. You got to keep it low cost and open source, meaning that the code is accessible for review for everyone. You don't just want one or two companies monopolizing it and not letting you see how it works. So in this implementation, it needs to be agnostic of the type of stimulation or sensor. And here we have a taxonomy of 3 different parts: sensor, transducer, and hybrid. Sensor is what records, transducer is what stimulates, and the hybrid is a device that can do both. So the sensor here can include like EEG, which I mentioned earlier, or MEG, or FNIRS, that is optical stimulation. We also can have a location and coordinate system, the 1020 international system, based on common proportions of dimensions between sizes of your head. So it can adjust to each person's individual head size. The transducer could be like focused ultrasound, TMS, electrical stimulation, haptic, that is like a vibrator or tactile feedback. And the properties could be like the location of the transducer, the period it takes to stimulate, the target range in the event you want to target a region instead of a specific 3-dimensional point, or the latency and timeout, how long it takes to deliver, or if you want to have a failure window for redelivery in case the initial one fails. So the sequence, the device starts up, you load the 1020 map of all the transducer, sensor, and hybrid device locations. You set your stimulation parameters, like where are you going to stimulate? Make sure it's calibrated for each use, the intensity, timeout, stuff like that, safety, security. Set your stimulation triggers, like if I think about moving my left hand, it'll stimulate focused ultrasound that'll affect my friend's left visual cortex, for example. You connect the device wirelessly or wired, maybe Bluetooth, as like the Open BCI works. Configure your session parameters like device verification, security, reconnection, and timeout. You send a test message because this is built on MQTT, which is a kind of Internet of Things protocol that's been used for decades, originally developed for SCADA in the 90s. You begin your recording for your sensors, and you can commence that session. That's the broad overview of how it's going to work. Now, my device target is release a documented GitHub repository, deploy and test AKLO on hardware and software, and implement a protocol with a human study. The uses we have are medical, like prosthetic feedback, especially in developing countries or to help with startups. Esports, like with gamers. Security, like guards looking at different monitors. Finance, like people looking at different Forex markets. Entertainment, like interacting over VR and other stuff. Now, conclusions. AKLO makes brain-to-brain interface from CBI and BCI. The good part is even though it's originally targeted, pun intended, for non-invasive, you also could adapt the same framework for invasive systems. And it's built on a proven and open source frameworks like MQTT and a lot of hobbyist grade stuff that's been around for a while. The reason I called it AKLO, by the way, before I take questions, is named for a fictional language by a writer named H.P. Lovecraft and some of his predecessors, like Ambrose Bierce and Robert Chambers. It's a way that various species could communicate without the need for spoken words. So in this system, you don't need a spoken language for direct communication. So I'll stop communication and I'll take some questions. Here's my references. Thanks.